Okay, so last time I talked for a long time about MG1Q. So I'm not sure you fully understand this. It's better to go back to just write a little bit, right? To think some concrete examples. But to really say, right? So MG1Q. So MG1Q is recurrent when mu is less than or equal to 1. So mu is defined like this.
তোমার ছাত্রগুলো তো ভগবান
Excuse me?
জানে কি অনির্বাণ চ্যাটার্জি কি করছে ভগবান জানে কার করোনা ওদের আবার কি করা হয় দেশে করোনা হয়ে হচ্ছে ধুর ওটা কোনো
Okay, you should mute all yourself if you don't want to ask questions. But it seems I cannot mute two people, three people. Maybe they don't have, they don't use the mute all. Okay. So if you want to ask questions, then you unmute yourself. But it seems for me I cannot unmute three people, but maybe they don't have audio connection or something. Okay. So for MG1Q, right, we showed last time. So if mu, the mean number, right, the mean number of customs and arrival during a service time, so it's bigger than 1. So then this is transient. So the idea is very simple, right? So if K is here is relatively large, right? And each time it's more likely to move. It's more likely to move to the right than to the left. So if you're starting from something very large, right, there's some possibility, right? The positive possibility you can never reach 0. Right? But this chain, right, the state space is Z, right? This chain actually is irreducible, which means, right, from any two state, from 0, you can reach to any positive numbers, right? From any positive numbers, they have positive probability you goes to 0, right? So it's irreducible chain. Okay. So if mu, right, if the mu is equals to 1 and or less 1, right, from our discussion on branching process, we can show, right, so in probability 1, you can always go from K to 0, right? So all the branching process will die out almost surely in finite time. So you can always move from K to 0. And of course, right, so you can always expect new customs, and from 0 to K, right, is always possible. So the chain is recurrent in the opposite case of this. Okay. So this is some proof using optimal stopping theory for non-negative super martingales. So this is for the case mu is bigger than is less than or equal to 1. So you can check the details, but I will skip that. So I will just start the discussion on stationary mirrors and stationary distributions. So stationary mirrors, right, is just stationary distribution, right, is just normalized, right? So it's just a mirror, probability mirror, right? So it's also a stationary mirror, but the total mass is 1, right? So let's consider Markov chain. Let's consider Markov chain. This is the state space, and this is transition probability, right? The probability you're going from state X to state Y, right? It's a transition probability. So we call a mirror mu stationary mirror, right? If this is true. So what does this mean, right? So you sum up with all possible state x, right? You're going from x to y, right? You get the probability mu x, right? Which is basically says, right? So if you run the chain, right, for one step, right, you ends with the same mirror, right? So this is the original mirror mu, right? And you run the state for one step, and you ends with the state mu, right? With the state mu as well. So if this is a finite Markov chain, right? So we know this very well, right? So P is just the transition probability matrix, transition matrix. And the stationary mirror is just the probability, not necessarily probability, it's just the left adding vector of this.
我的也好了。
Yeah, you have questions?
然后现在可以了吗？
Yeah.
啊
Yeah.
，model 可以了吗？你已经跑好了。哦，好，那我关了。
Okay. It's weird today, right? Okay. Yeah, there are two people I cannot unmute, but maybe they cannot use in their audio. Okay. But okay. So I just go a little bit use this slides, then I will come back. Okay. So so mu is the stationary mirror, right? U is the stationary mirror. So mu p equals to mu, right? So you run the Markov chain for one step, right? It ends with the same distribution, not necessarily probability distribution. It ends with the same mirror mu, right? So if we run this several times, right? So this is starting from mirror, initial mirror mu, right? We ends with the same mirror, right? So, and we can run this several times, right? So we get from starting from initial mirror mu, and okay, so this is a y, it's a typo. So xn equals y is also equals to mu y. Right? It's just definition of stationary mirror. So if this stationary mirror, right, mu is normalized to be a probability mirror, and because it's a stationary distribution. Right? So the definition is very easier, and we can. So there are many examples, right? So the easiest example is the random walk, right? For the random walk in d dimension, we can just choose the transition probability to be this fy minus x. So f is just the probability mass function for each Casa I, right? Casa I is IID, right? You're starting from x0 and each increment is Casa I. And f is the probability mass function. Right? So we can just choose, right? You can check this is true. We can just choose mu x is a constant function, 1, constant function, 1. Okay. So this really gives you the stationary mirror, right? Because right, if you multiply mu x, right, sum up with multiply this with mu x, right, sum up with x. So basically, you just sum everything with respect to x, right? So you run all possible x, right? This is give you give you 1, right? Give you 1, right? It ends with the same thing. Okay. So this, I go kind of a little bit too fast, but and that should be reasonable because you also you already saw those examples before. Okay, so here is a diagram for birth, death, birth and death chain. So I postpone one problem to next Wednesday. So it's on the birth and death chain. So it's the problem in last section, right? In last section. Yeah, let me just finish this. So that problem, you can just use theory. You can just use theory. So excuse me? So if you have questions, unmute yourself, otherwise. I should unmute all. Oh, I should mute all.
I think.
It's very weird. I can, for some people, I cannot mute. Okay, let me check. So Zixianzhou, you are there? Zixianzhou, are you there? Yeah, okay. So it's weird because sometimes there's noise, right? So I unmute all, but I cannot mute yours. Now I can. Okay. 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 So now fine. If you really have a question, you can unmute yourself. Yeah, maybe next time I should try to using a different meeting ID and with password. So in case some people just hack in. Okay. So so there's a homework problem that I postponed. So this is it's not really a probability problem. It's really just a calculus problem. But you need to use the theory. So you need to do a little bit of reading, and so this is just an application of theory 5.3.11. So the exercise 5.3.4 is just the application of theory 5.3.11. So the birth and death chain is very important. Use you a lot of places, right? So for instance, random walk actually just one particular application, right? And you can even think some Q model are also, you can also represent it as the birth and death chain. So I talk about birth and chain, right? In the reversible mirror setting. But for the homework problem, it's really a calculus problem. It's just checking the condition in the theory 5.3.11. Yeah. So this is not, let's introduce another notion. It's called reversible mirror. It's more specific, it's more restrictive than stationary mirror. So what do we mean by reversible? So as this condition is satisfied, so mu x from px from x to y, right, equals to mu y times from y to x. This is called detailed balance condition. So what does this mean, right? So this is the mass enter state x. So this is the possibility, right? You go from x to y, right? So you can think this part as the mass you send from x to y, right? And this is the mass you send from y to x. So this is called detailed balance condition, right? Right, the mass you send from x to y equals to the mass you send from y to x, right? If this condition is satisfied, right? If this condition is satisfied, if the condition star is satisfied, we sum up with respect x, we really can get this condition. We really can get this condition. Is here is more specific, right? Here is more specific. Yeah. Yeah. So in this birth and death chain, right? So let's write the probability going from x to x plus 1 as px. So the probability going from x to x plus 1 is px. The probability going from x to x minus 1 is qx, right? And etc., right? So all the state is 0, 1, 2, 3, right? It's all the natural numbers, natural integers. Okay. I mean, px, So px plus qx is not necessarily one. You might have the probability just stay at rx, right? So px plus qx is not necessarily one, right? But it should be less than one. Okay, so we want to compute one reversible measure, right? So if this condition, right, is called detailed balance condition is satisfied, right? We call this measure mu a reversible measure. We can easily compute a reversible measure for this birth and death chain. So the idea is very simple, right? So if it's detailed balanced, right? So from X, right? So there's a mass transformation, the mass transfer, right, between X and X plus one. If it's a reversible measure, right? So the mass sending from X plus one should be equal to the mass sending from plus X, right? So this is just the condition we write here. If you do a basic algebra, right, you can just write you can choose mu zero, right? Mu zero equals one. So mu one, you can just use from this condition, you can calculate that. So multiply those together, right, by induction, right, you can just write mu k. Right, so it's very easy, right, to compute one example, reversible measure. Okay. Okay, I will start to use iPad, right? Otherwise, it might be too quick. Well, since I don't want to be too quick. Okay, so this is a Kolmogorov cycle condition. So we want to in a lot of applications, right? So we want so we want to share. So we want to a Markov chain, right? So so in simulation, right, there's a very famous techniques, right, numerical method or called MCMC, right? Monte Carlo Markov chain, Monte Carlo. So it's very in that setting, actually, it's very important to have a reversible measure to design a Markov chain with a reversible measure. So basically, those Markov chain, given a measure mu, it should be reversible. Right? It going from time 0 to time n. Right? If you reverse that, it's basically the same. Okay. So to guarantee, right, we will have a Markov chain with reversible measure, right? We need we need to check several conditions, right? So this is guaranteed by Kolmogorov theory. I will use my notes. Okay. So I skip a lot already. So it's better just to read, go through all the textbooks, right? I won't post the homework problem, but actually this part is more important. Not more important, right? This part is, I mean, so if you just see very easy setting, like the link I posted earlier. So we just study like finite state Markov chain, right? So you have a probability transition matrix. So everything can be reduced to study of P to N, right? So the asymptotic behavior of a stochastic matrix. So that actually is a very classical problem. So many things I talked in this class, you have some counterpart in numerical, like linear algebra. But the discussion in this lecture actually is more general. But if you know some concrete example from finite state Markov chain, right, maybe just two states or several, it's more easy to understand. So I still, right, if you don't go to, you can use the MIT open courseware lecture, like the videos, right, to do the review. But we will just start on a more general discussion. Sometimes I will give you examples. So this is very important, right? On like which cases we can have reversible measures. Okay. So this is called Kolmogorov cycle condition. So of course, right? So there are some chains, right? It's very easy, right? You know they won't have. So give you an example, right? So let's say, so the state one have one probability goes to itself and have one probability go to state one, right? And state one is absorbing. So in this state, right? So no, of course, no reversible measures. Right, so this is easy to see. But as I told you, right, so we can very easily write a stationary mirror, right? So the stationary mirror is just a mu0, mu1, right? I mean, it's very easy to write. We can even write a stationary distribution, right? Why? Right, because here, so 0, right, and each time iteration, so there's 1/2 probability you go to 1, right, and stay there forever. So in the end, right, so you can think right, the stationary mirror, right, is one like a long time distribution, but it's not necessarily long time distribution, but long time distribution, a long time limit or equilibrium is can give you one stationary mirror or distribution. So in this case, in particular, we can choose this, right? So this is a stationary mirror. This is stationary mirror, but of course not reversible. So this chain, so this chain is not irreducible. Is not it's called irreducible, right? It's not irreducible. This chain is not irreducible. You can move from 0 to 1, right? But you cannot move 1 to 0, right? So if the chain is not irreducible, right? So usually we cannot say a lot, right? So usually so in the following discussion, most of the time we just assume everything is useful. So let's write the theory. So this theory, of course, is due to Kolmogorov. So suppose P, right? So P is transition matrix. So sometimes we should write S, right? P. So S is the state space. P is the transition matrix. Is irreducible. Okay. So irreducible means what, right? So for any two state, you can access each other, right? You can access each other. So a necessary and sufficient condition for the existence of a reversible mirror is the following. So there are two conditions. So first, so if you from X to Y, right, and one step, so then Pyx also bigger than 0, also bigger than 0. So second, so for any loop, so closed loop, right? So for any loop, x0, x1, xn, so xn actually equals to x0. And also this loop is possible, right? So this loop is possible means the following. That from Pxi, so this is positive. So this means, right, from any two step, from x is possible, right? In one step, from x1 to x2 is possible, etc. Right? So with this condition, excuse me?
We can see your screen.
You cannot see the screen?
Your screen froze. We can't right further.
Yeah.
So now you can see that?
Yeah.
See?
Well, I think now it's fine, but
now it's fine. Okay, sure. Okay, so
scroll up a little bit. Okay.
Hold on.
Yeah. So this is okay. Maybe I start here.
Yeah.
Okay.
Yes, start from the theorem. Yeah.
Yeah. So the statement is right. We want to give a necessary efficient condition to guarantee Markov chain is has reversible mirror. So this is usually is needed when you design MCS, so Markov chain or Markov chain Monte Carlo method. Okay. Yeah. So the necessary and the sufficient condition is just the first, right? The first one is if you can move from X to Y, right? So it's just one step, right? One step probability. If this is big, then you can move from Y to X. Then you can move Y from X. The next assumption is the following. Maybe read this. So this actually is called a cycle condition. So Pxi minus xi over Pxi xi equal to 1. Yeah. So this is the condition. Then, right. So this is so as long as these two conditions are satisfied, we can actually write explicitly the condition, the reversible mirror. Okay. So how to do that? Okay, how to do that? So I will just write the proof below. So I won't talk about details, but I just tells you the idea, right? First, let's say the necessary part. So what's the necessary part, right? Let's say we already have mu. So this is reversible. So it means we have this detailed balance condition. Let's say we assume there exists mu, right? Mu is reversible mirror, right? So in this case, so since S is irreducible. Since S is irreducible, actually for any X is true. So as long as mu is stationary mirror. So by S is reducible as long as mu is stationary, so we know, so this should be bigger than 0. So why? So let's just consider the following things. So let's consider two sets A and B. A and B. So and A union B is just S. So let's choose one X here and one Y here, right? So A is all those set such that mu Y bigger than 0. And is the counterpart, right? So B is all the set such that so mu X equals to 0. Okay. So by this condition, right, by star, since mu X equals to 0, right, so this will be 0. And so this is positive, right? So this should be 0, right? So that means so Pyx equals to 0. Pyx equals 0. But this, from this part, we don't know, right? It might be positive, but it might be not, right? So you can, so it's very easy to believe the following things, right? So since all the, so since for any point here, right, for any point here, you can never go back to here, right? But from mass from state here, you can go to here, or maybe not, right? So if here is all 0, right? So then these two actually are disjoint, right? It's not accessible from each other. But it is 0, right? So from X, from points in B, right, you can move to A, but you can never come back, right? So this is not accessible, right? It's not reducible, right? From A, you cannot go to B, right? So it's contradict. So if there exists this type of state, right? So then this S is not irreducible. Right? So by irreducibility, right, we can show, we know immediately. So this is this actually is positive. Okay. So since these are all positive, right? Since these are all positive, right? These are positive, these are positive, right? So if this is bigger than 0, of course, this is bigger than 0, right? So immediately we can get the first condition is satisfied, right? So this is trivial. So second condition, right? So we need to check this condition, right? We need to check this condition. Let me check 2. So how to check 2, right? Let's draw a picture, right? So let's say this is x0, x1, x2, x3. Let's just say is xn, and you can go back, right? So so from the assumption of the loop, right? So you can go from x0 to 1, you can go from x1 to x2, right? So this is possible. So which is just our assumption. So assumption is writing in the reverse order. But if this is possible, right? So then this is also possible. This is also possible. This is also possible, right? So the assumption, our assumption is this, right? Px1 x0, px2 x1, right? Px3 x2 times px0 x3. Am I right? X0, x2, x1. Yeah, this is example. As long as this is true, we want to show the following. Let's just using our using general n, right? So this pxi minus 1, pxi minus 1 xi. So we want to show this is 1, right? So this is our goal. This is our goal, right? This is our goal. yeah, it's the same, right? So it's the same. I mean, even the order is changed, then doesn't matter. Right, so from X, yeah, the order is different, but I mean, it doesn't really matter, right? Okay, it doesn't really matter. So why this is true, right? Why this is true? It's very easy to see, right? So why? Because the following, right? So I just write, let's say we write Pxi, xi minus 1 over Pxi minus 1 xi. So what's this, right? So actually, right, so if we write, if we use the balanced condition, so if you move from xi, right, and you move from xi minus 1, right, so this is 1, right? So this is balanced condition, balanced condition. This is balanced condition. From this balanced condition, we can just write the ratio. We can just write the ratio. So Pxi minus 1 xi. So which is just mu xi minus 1 over mu xi. Right. So we can, so then we just take the product, right? Take the product because it's a loop, right? Because it's a loop, and this is just the right, so the end point over the first point, right? If you multiply this together, right, by telescoping, you just get 1, right? Just multiply together, so we can get 1. So then we get 2, right? So it's not very hard, right? So from the proof, right? From this proof, we can actually directly give. We just write here. You can details later, but from our discussion here, we can directly write one possible definition. So let's say we can change. We can choose x0. We can just choose one x0 and set this value to be 1. Right? So later we just define x. We just define xn, right? Let's say xn is just x. And so this is x0, right? So it's connected, right? x1, x2, right? Let's say xn. So we can just define the value and xn as the product. As the product. So I should be careful here. Might be the order matters. So let's just. So we define this as the product. P xi minus 1 xi over P xi minus 1. Okay. So you can check very easily, right? So this is, what does this mean? So maybe I write here. So this mu x just fine. So this is x0 like this. Let's say here is x. It's just defined by the product of go there and go back and take the ratio and multiply, go there and go back, times the ratio, go there and come back and take the ratio, then multiply together, right? So by the ratio, by the cycle condition, so we can really check. So this is well defined. So this is well defined. So why, right? Another path, let's say, have another path, you go from here. So you go in from this path, and actually, right, you take the same product, right, go as the ratio, right? So it's the same, because if you going like this, you get 1, right? If you're going like the whole loop, you get 1. So mu x is well defined, and actually by this definition, you can really check, right? So if this is y, you can really check mu x time, so there's that this is x, this is y. So mu x times, so p going from x to y, right? Go this direction and come back. So p y x. So then you get the definition of mu y. Okay. So this is exactly the best condition. So this is exactly balanced condition. So we are done, right? So it's so the necessary part is actually embedded. So necessary, so sufficient part can be can be can be can be can be put. You can get the proof by sufficient can be motivated from the necessary part. Okay. Okay. Is it clear? Okay. So let's just emphasize one. Maybe I just write. So yes. So this is a chromograph cycle theory, which basically says you have a cycle, right? You have a cycle, any cycle. So you go in this way, and then you go in this way. So the probability, transition probability is the same. So you go to this cycle, right? You take the transition probability together, right? So then you go from this cycle, right? So the transition probability is the same for any loop, So so then you can have reversible mirrors, right? You can have reversible mirrors. Okay. Yeah. Yeah, that's it. Yeah. Yeah. So, I mean, of course, the loop, right? Loop length should be bigger than or equal to 3, right? So otherwise it's not. So then you can have a reversible mirror. Okay. So as I said before, right? So reversible mirror is a very specific, but the stationary mirror is more easy to have. So actually, for many Markov chains, you can construct stationary mirrors, right? So usually, right? So since we don't have a lot of time, I should talk something like in big picture. So stationary mirror, right? Like existence. Right? So those problems, right? There are several problems, right? So first, there are problems on existence. There are problems on uniqueness, right? So if we know a Markov chain has unique. So then, do we know, right? So can we have some uniqueness, right? In certain sense, right? Or we can ask, right? So as n goes to infinity, so does this n, right? Mu n converge to something, right? Converge to something as n goes to infinity, right? Or is the mirror, right? And n step converge to something, or so the transition probability from x to y, right? But for n step, converge to something or not. Right. So those are basic questions, right? You want to study, right, dynamical system or PDE or any, or even probability. So those are our basic questions. We can answer several of them, right? For this setting, the stationary mirrors. Like, can we construct one stationary mirror, right? So on what sense can we have uniqueness, right? And also, right, can we have stationary distribution, right? So those two actually are not that the same, because sometimes you can have stationary mirror, but it's not a probability distribution, right? It's not a finite mirror, right? So mu, so for stationary mirror, right, mu on the whole space, right, on the whole space, so this might be infinity, right? A good example is the following, right? So it's the following. So so let's consider, right? So ZD, right? D and a random walk. Let's consider a random walk. So we know, right? We know. So actually, the stationary, because random walk, right? Let's say simple random walk, right? Symmetric, simple random walk. So we can just choose for each. So this is example I just showed you in the very beginning. Okay, so this gives you a stationary mirror, but this is not not, you cannot normalize it, right? So cannot be normalized to a probability distribution. As we know, right? As we know, right? For simple random walk, right? So in dimension D or 2, right? So this is recurrent. So we know, right? Simple random walk is reducible, right? So of course this is irreducible. So from any state you can move to other state. But if D equals to 3, right? This is transient. We proved this earlier, right? Maybe in last year. So, but this tells us, right? This tells us, right? Even, right? So, Markov chain is transient, right? You can still hope stationary mirror, right? So, stationary mirror is a general notion, right? So it's much more general than reversible mirrors. Okay, so I will just give you an example of construction of a stationary mirror, right? So it give you a existence, right? So, and first we should know the existence. Okay, so this is the first theory. It's called existence. Existence of a stationary mirror. Existence of stationary mirror. Okay, so let me state this first, right? So when we are done, you can easily see, right? So why this is intuitive, right? Intuitively right. So let's consider, right? So so the setting automatically there, right? So we have S, we have a Markov chain, right? We have a Markov chain defined there with transition probability P. So let's choose S, which is a recurrent state. So let's assume this Markov chain has a recurrent state. And we define a stopping time. We define a stopping time. So which is the time the Markov chain visit X. Since this is recurrent, right? So since X is recurrent, right? So starting from any point, not from any point, right? So that's wrong. So from, right, you can always return, right? So recurrent actually means this, right? Recurrent means this. So you're starting from X, you can always return to X in finite time, right? With full probability, right? So T is just the stopping time. T is the stopping time. I think we're starting from X0, right? So otherwise it's, yeah, we're starting from X0. But it's not right here, right? So, yeah, so I should, so this T, right? So X0 equals 0, right? X0, which starting from X0. Okay. But this really doesn't matter, right? So it matters or it doesn't matter. Yeah, wait, let me double check this. So the idea is just, okay, you're counting all the time you spend and why. Okay, so the result actually is it's really starting from x, but it's not reflected here, but it's reflected definition so of mu x. So mu x is a measure we constructed, which really gives you the stationary measure. So what does it mean, right? So if we're starting from x, right? So x0 actually just 0. And we counting all the number of visits. We're counting all the number of visits to y. And so this gives you, right? So this is really the average number. So this is average number of visits to y. So in time, in those time, 1, right, 0, 1, 2, t minus 1. So this is just the average of the time, right, you spend before you hit x in y, right? So you have, right, the t is a random variable, it's a stopping time, right? If you hit x, right, you stop there. But in the first t times, right, we counting the average you spend is the average time you spend and y, and this gives you the mirror. This gives you the mirror. So you can compute, right? So you can compute by expanding the number of all t, right, all possible choice of the stopping time, right, the expectation and this. But since we won't talk about proof, it's not really useful here, right? So it's more useful if we see the proof. But here, right, is really, the definition is really simple, right? The stationary measure is defined by the average time you spend and y before you visited x, This actually makes perfect sense, right? In particular, right, so you can check. So if you just want to counting the mass, the probability and x, so this is just a 1, right? This is just a 1. So because here, right, so t is the stopping time you visit x, there's only one there, right? It's only one there, right, which is the initial state, right? So it's always 1, right? You integrate a constant function, right? So you get 1. Okay. So, right, from this construction, right, actually we can see vividly, right? So so we can define mu x. We can define a family of mu x. So these are all, right, all stationary mirrors. So those are all stationary mirrors for Markov chain, right, for S, right? So we can probably have many stationary mirrors for one Markov chain, right? You can see a lot of examples, right? For instance, right, let's just see a very easy example. Let's say we have 1, 2, and we have a state 3, right? And we have a state 5 and 4, right? So let's say this is just 1/2, okay? Sorry. 1/2, and this state goes to, okay, 1/2, right? This state go to 1/2, right? This state goes to 1, right? This state goes to itself, right? And yeah. Okay. So this is 0, right? Okay. So this is transient state, right? So you can very easily check, right? This is transient. So maybe let's give let's change a bit. Let's give 0.7. Okay, 0.3, right? 0.3. This is 0.7. Okay. So this is transient, and these two are recurrent blocks. Are recurrent. These two are recurrent, and right. If you choose different x, right? If you choose x as 5, and you choose x as 4, or you choose this different recurrent block, so the mirror you choose should be different, right? So the mirror actually changes with possible x. Right? This S, right? So S actually is not, but this makes sense, right? Because this S, this Markov chain is not reducible, right? Why, right? From this state, you cannot reach 5, right? From 5, you cannot reach, you cannot, right? So so as the decomposition theory said before, right? So to study Markov chain, so most of the time is sufficient, right? Just stay in this block, right? Just stay in this block, right? Most time. So the following discussion, we would really want to seek uniqueness. So we need to add more assumptions, right? For instance, we need S to be irreducible. Right? So otherwise, we cannot expect too much. Right? So I won't talk about the proof of this existence part, right? Existence part, but it's very easy to see, right? Intuitively. I just say several words about that proof. So, okay, so let's say mu x is a mirror, right? Mu x is a mirror. We want to show this is a stationary mirror, right? So if this is stationary, what does this mean, right? If this is stationary, this should mean the following, right? Y, right? Y should equal to mu x, right? Then move from z to y. So if mu x is stationary mirror, right? We should show this is true. Right? This is our goal. So I just explain intuitive idea, right? So let's write this part. Let's define this part as mu s py, right? It's just a definition, and we want to show this equals to that, right? Okay. So actually, right, this term, right? We just this intuitively. What does this mean? Right? Intuitively, this means the expected number of visits to y in. So okay, so this means right, you first visit z, right? Then you transit y, right? So z is the average number you visit z, right? In 0, 1 to t minus 1, and here. So because y is in the lab, right? So it's the average number you visit y in this. So this actually equals to the average visit to y in 0, 1, 2 to t minus 1. So by x0 equals to xt equals to x. Because x0 equals to xt, right? Because x0 equals to xt equals to x, right? So if you just shift a little bit, right? Just shift to the right one step, right? Since 0, right, is x, right? So this is x, right? So it doesn't change. It doesn't change. Of course, this is just the intuitive idea, right? You need to see the proof, right? You need to see the proof. But basically say, right, this is exactly the same, right? Because x equals to xt equals to x. And this is just, okay, your first step, you go to z and you move from z to y, right? So, yeah. So this is the basic idea, but it's not a rigorous proof. So intuitive, this actually makes a lot of sense, right? So it's just the time you spend in Y, right, before you visit X. Since X is current, right, you always comes back, right? And this gives you the measure, right? So if you spend more time at Y, right, definitely Y should have more weights, right? Okay. So this is the existent part, right? So as I said before, right, so if we want to have some type of uniqueness, right, we need S is irreducible, right? So now let's just state one uniqueness result, and probably we don't have a lot of time, and we will just go maybe list several results so you can check later. Okay, so one uniqueness result theory. So actually, we discussed here, right? I'm very sure it should be called param Frobenius. So I'm not sure my is right. I need to check my spelling. It's called sorry. Okay. So this is in spirit. In spirit, it should call the param Frobenius. But this took like 100 years ago, mathematician, they did this for P, right? It's a matrix, right? Let's say M by M matrix. So if you search param Frobenius theory, right, you find a lot of literature, right? So I'm sure people in numerical analysis, right, in statistics, there, right, this is well-known things, right? But our theory, so the theory I will tell you, right, is kind of a generalized version of that, right? Essentially, it's just a param Frobenius theory. Okay, so let's understand this. So if P, right, so P is the transition probability. If P is irreducible, right, so don't really distinguish as Markov chain or transition probability, right? Because if I give you transition probability, I already told you the state space, right? I'll also give you the transition probability, right? So actually, I told you everything. So if P is irreducible and recurrent, right? Since recurrence is contagious, so all states, so actually all states are recurrent. So under this setting, we basically just consider one recurrent block, right? One recurrent cluster. So then the stationary mirror. So then the stationary mirror is, I mean, if you just say unique is not true, right? Up to a constant multiplier, right? Multiplier. So we can always multiply that, right? Okay. Yeah. So that's it, right? That's the statement. Need to close. Okay, up to a constant multiplier. So I want to prove this. I won't prove this. I won't prove this. But I want to ask a question, right? So is recurrent here essential? Is recurrent here essential or not? You can check the proof, right? But let me ask you a question. let me ask you a question. Is recurrent here recurrence here crucial or not? You check the proof. So we kind of, so the proof is, okay, so we use the previous construction, right? By the previous construction, the existence part, which is here, right? So this formula gives us one possible stationary mirror, and we just consider all other stationary mirror, right? We keep expanding those stationary mirror, and we can show we can show they are equal to the stationary mirror we constructed, right? We just constructed it here. So everything is equals to the stationary mirror we constructed there up to a constant, right? So that's basically the idea. It's actually a very nice proof. Right? We really need the irreducibility here, and we really need the recurrent here, right? Otherwise, we cannot construct those stationary mirror. But as I said, right? So for certain, for instance, simple random work in 3 dimension, they have stationary mirror, right? But stationary mirror, I mean, even you have transient states, you have stationary mirror. So in that case, maybe it's really not unique. Right? It's really not unique. Maybe on thing you can also show uniqueness. So for instance, we have very strong symmetry, right? So we have very strong symmetry. So like simple random walk in three-dimensional ZD. So probably it's unique, right? Up to a constant, or up to a scale constant. Okay. So this is a uniqueness theory. So irreducible, I just make a remark, right? Irreducible, and I mean recurrent, you know, right? So irreducible is just, I mean, for let's say if P just equals to all Pij, right, is the transition probably from I, right? This is a mix or infinite dimensional matrix. So P is irreducible, it just means this, right? Just means, right, for each ij, right, 2 states, right, is each 2 state, right, we can always find a number n equal, which probably depends on nj, right, such that we can move from I to j. We can move from I to j, right? So this theory, right? So I mean, this theory probably not really called a Perron Frobenius. Maybe we should combine the following theory we see. But basically said the same thing. Right? So basically says if P is irreducible, right? Then the stationary mirror, right? Stationary mirror actually just the eigenvalue, eigenvector, right? So basically the eigenvector is unique. Yeah, something like. I will skip this. We have 10 minutes. I think we can still cover the remaining and listing in this section. Okay, so the following theory. So let's show a very easy theory. So if there exists a stationary distribution, so if a Markov chain has a stationary distribution, right? Stationary distribution means it's a probability distribution, right? So then all states with pi y, right? Pi is a stationary distribution, because this is pi, right? So all states with pi y bigger than 0 are recurrent. All states y are recurrent. So what does this say, right? It says, okay, no matter what, right? So any Markov chain, right? As long as you have a distribution, so as long as the stationary mirror, right, is positive, right? So then this state is recurrent. It's a very easy to show. This theory is very easy to show. So I will just write, because in last Monday, this Monday, I I want to use something I stated in the very beginning of the last this Monday's lecture. So pi is a stationary distribution, right? So p is a transition probability. So we can iterate this, right? I mean, this is not really a matrix multiplication, right? It's just a shorthand notation, right? But if you think of this matrix multiplication, it's also true. Right? So this really means, right? You iterate the matrix for n times, right? You same matrix distribution, right? It's a stationary, right? So if you sum up with x, right? And this is n-step transition probability, so we get pi y. And let's assume this is bigger than 0, right? And this equation, right, is true for all n, right? So n actually now equals to 1, 2, 3, etc., right? So we can sum up with n, right? So sum up with n. So p n x y sum up with x, right? So sum up with n. So this is infinite, right? So because pi y equals to is positive, right? So if we sum up, this is infinite. And we can use in Fubini because here everything is positive or 0, right? So we can use Fubini. We can sum up with n first. Okay. So what's that? What's this? Right? What's this? So this is pi x. So calculation, right, in this Monday, right, so just starting from x, ny. Right. So this is finite. So if y is transient, right? So this is contradiction, right? Because this is infinite, right? Then that means y must be recurrent, right? So false. So is recurrent. First y is recurrent. Okay, so this tells you, right? If you have a distribution and a stationary distribution, and then y is has positive mass, so this state should be recurrent, right? This state should be recurrent. Okay, so okay, so we almost done, but I need to say one more theory, right? So you need to say one more theory. Is right. So if P is reducible, and P has a stationary distribution pi, So what does this mean, right? So if this is just a setting, but I want to say, right, what does this mean, right? So if P is a Markov chain has a error pi, right? Pi is a probability distribution, right? So at some point, right? So there exists a y such that pi y is bigger than 0, right? Because it's a stationary distribution. So by our theory here, right, by previous theory, right, if it has a stationary distribution and pi y is bigger than 0, so this means pi y, y is recurrent. So actually, right, since P is irreducible, right, so P is reducible, so actually every X is that's not enough, right? So this is just a one corollary, right? So this is one corollary. So I want to point out, right, two corollary. I mean, just from the setting, we haven't said the result. So if P is irreducible and P has a stationary distribution, then actually for any y, So pi y is bigger than 0. So the discussion is exactly as before when we prove the Kolmogorov cycle theory. So since P is reducible, right? So actually any state. So for the stationary distribution is a stationary mirror, right? So actually this is true for any. This is true for any state. So anyway, so this is not done yet. So the theory is really we can write, right? So so this is just what we draw from there, right? So every state is recurrent, and every state has a positive mass, right? Positive mass in the stationary distribution state. And by our uniqueness result, we have a uniqueness result, right? So this is our uniqueness result, right? So we have the stationary mirror is unique up to a constant, right? So under our setting, under this setting, right, we should have uniqueness. And also, right, this is a distribution, right? So the scalar, so really doesn't matter because here we have probability distribution. So it's unique, it's really unique. And we can, in particular, write this formula. So it's just this. So the stationary distribution, we can write the explicit formula, right? It's just the reciprocal of, okay, EX, right? You're starting from X and you can the expectation you spend on X, right? So then that's it. So EX, TX, EX, TX equals to the average, I mean, just the meaning, right? The average time you spend on X, right? So this makes sense, right? Not the average time you spend on X. You spend before you visit X. So the average time you spend before hitting X. So this makes sense, right? It's obvious almost. So if you spend more time before you X, right? So actually means, right, spend more time means X is visited less frequently. So this becomes small. So if this is small, right? If this is small, right? So this becomes bigger, right? That means you visit the X, right, many times, right, more frequently, right? So this should be explained as the frequency of visiting X, right? So it's just an intuitive explanation, right? It should be explained as this. I think maybe it's better to call this, right? It's better to call this Perron-Frobenius, right? I think this is more close to the classical result of the Frobenius theory. Perron-Frobenius theory. Okay. So from here, I mean, if you have other things, you can go. I just tell several minutes. From here, we can discuss Tx, right? So if X is recurrent, right? So definitely, right? Since X is recurrent, right? So if you're starting from X, so you go back to X, right? So it's probably the 1, right? Infinite time. So we can still distinguish this, right? We take the expectation, right? So the expectation can be infinite, right? So if the expectation is infinite, so that means pi x equals to 0, right? So we call this case, right? We call this case now recurrent. So if Ex, Tx less than infinity, right? So pi x actually is positive. So this case is called positive recurrent. It's better to write like this, right? It's better to write like this because this is more general, right? This is more general definition, not necessarily in the irreducible setting. But in the if S is irreducible, if S is irreducible, so then we have the following characterization. Then the following are equivalent. The following are equivalent. So first, right? So if X in S, so X in S, so there exists X in S is positive recurrent. So like this, okay, like this setting. So the following, so then there exists a stationary distribution. So if we have one state is a positive recurrent, we can construct a stationary distribution pi. And if we have a stationary distribution pi and combined is with irreducibility, then by the previous theory, we know, so every state is positive recurrent. So every state is positive recurrent, right? And definitely, right, this implies that, right? 3 implies 3. So all these are equivalent. Right? It's almost the complete characterization for irreducible and recurrent Markov chain. And we don't have time to talk about the asymptotic behavior. So this is the existence and uniqueness. And their discussion on asymptotic behavior on our Markov chains. Okay. So I won't assign homework problem, but you are recommended to read that and write some notes on the next section. So in particular, right, we want to understand, right? So under what condition? So let's say Pn xy. So Pn xy, we want to, so let's say we have pi, right? We have irreducibility. Let's say we have irreducibility. And also we have recurrent, right? So let's assume strong assumption, recurrence. So can we show something, like can we show, right, as n goes to infinity, this is good, right? So this is the distribution, stationary. So this is basically what we want to do, right? So so in the lecture, but I won't talk about this. We don't have time. So as I said, right, you have other things, you can leave the meeting. That's fine. So this is the theory we want to show. This says, but I want to tell you the meaning, right? Just the meaning of this, right? What does this really mean, right? So this means, so as n becomes large, right? So x is the initial state. So as x becomes large, right, the initial state really doesn't matter. So you lose memory of your initial state. I mean, this has a lot of applications, right? So this definitely has a relation, right? It has similar flavors as in ergodic theory. Mix, right? Mixing things, right? So basically, right? So I mean, ergodic theory says more or less close to here, but more close to this, right? If you have a function fn. Not fn, you have a function and a map, right? It's starting from x, you keep mapping this many times and you compose with a function. And so you sum from 1 to n. And so this is called time average. It's a time average. And in the end, you convert to something, it's average f on the space x. So it's like average. Ergodic theory, like, as t goes to infinity, and time goes to infinity, So the average of your trajectory gives you a good prediction of the space, right? So this is the space average, right? And this is a time average, right? You know the sequence of your trajectory, right? So those are all the same, right? So I suggest you just read this proof, right? This proof. By coupling, right, it's a very nice technique. Right? So you construct two stochastic process and compare those two stochastic process. And in the end, it can give you this, right? So similar techniques we use, we talk about a person process. It's good, you definitely should know this, right? You want to want something on Markov chain, you definitely, it's good if you read through all these chapters. I will stop. Questions I can answer, but otherwise I will just stop here. Yeah. Yeah, you can just unmute yourself if you want to ask a question.
Jenfu,
Yeah.
just to be sure, you sent an announcement yesterday saying that the last question of our homework need not to be turned in today.
You should turn in at some time, but yeah, I mean you can turn in, but since I say it won't be graded, so it doesn't make a difference, right?
Okay, so it's not mandatory to turn in.
Yeah, you can. It's not since I say it won't be graded, so.
Okay.
Because I don't talk about this before today's lecture. It's not really a hard problem. It's basically a calculus problem.
Mm-hmm.
But the calculations are a little bit, yeah, but it's definitely you can do that, right? Using Taylor or using other things.
All right.
Yeah, yeah.
Okay. Thanks.
Yeah. Yeah, maybe I stop call, so you have question I can still answer, but yeah, stop.